Hello, in this video, we are going to take a look at a pretty common problem, and that is finding the pH of an acid-base mixture. In this particular case, we're going to be looking at a strong acid with a strong base. And sometimes you end up with a pH of 7. That's if you're at the equivalence point. This particular example is not at the equivalence point. So what you have to do is figure out what's left over of the two starting materials. And so what I've done is over the years, I came up with a set of 6 steps that you can follow. This should work for pretty much any acid-base problem, whether it's a strong acid, strong base, or a weak acid, strong base, or a weak base, strong acid, whatever combination you might have. And you can follow these 6 steps, and that'll pretty much take you through how to get the pH of any problem. Now, some of the steps change a little bit in terms of how involved they might be, especially like step number 6, where it just says calculate the pH. Sometimes that gets a little more involved, but let's try this one because should be one of the easier ones. So we're going to start with step number 1 here, which is write the equation. So in this case, we have HClO4, which is one of the common 6 strong acids. My students, I usually have them learn these the 6 strong acids, things like HCl and HBr and HNO3, stuff like that. So HClO4, this is perchloric acid, one of the 6 strong acids, and then we're reacting it with lithium hydroxide, which is one of the 6, or not 6, but one of the strong bases that are out there. There's more than just 6 of those. And so that's going to be our reaction. Now, when I write the products, I like to write the salt product as the separate ions. That way we can look at each ion individually in the next step. So we're going to get some lithium ion from the lithium hydroxide. We'll get some perchlorate ion, ClO4-, from the perchloric acid that we started with. And then the other product here is just going to be water from this. So again, what you learn in Gen Chem 1 typically is you write that salt together, you balance out the positive and negative charge. I like to write them separately here because sometimes one or the other of those ions might affect the pH. So we need to keep track of that. Next step is to identify the pH players. And so for this step, what I do is I go substance by substance, including those ions, and I ask myself, if that was the only thing present in solution, would that affect the pH of that? And so HClO4 is a strong acid. It's definitely going to affect the pH. So I'm going to underline that one and keep track of that. Lithium hydroxide, that's a strong base. Now, this comes back to you being able to recognize strong acids and strong bases. All right, and I've got a different video that explains how to do that. So part of this is being able to recognize that HClO4 is one of the 6 strong acids, recognizing that lithium hydroxide, LiOH, is one of the strong bases out there. All right, then let's look at these ions. The lithium ion just by itself, most metal ions, especially group 1 and group 2 from the first column and the second column of the periodic table, they don't typically affect the pH. There's one that does a little bit, but we'll get to that one later on. But lithium definitely does not affect the pH just by itself that way. All right, lithium ion. And then the same thing for the perchlorate ion. It does not. Remember, the stronger an acid is, the weaker its conjugate is, or conjugate base would be. And the same is true for conjugate acids of bases. The stronger the base is, the weaker its conjugate acid will be. And so you could think of lithium ion and perchlorate ion as the conjugates of these strong substances. They are the strongest substances you can have in water. That means these are so weak, they're actually weaker acids and bases than water. The only time you'd worry about the water over here is if it was the only thing left in solution. All right, if everything else had gone away, then the water would just give you a pH of 7. But water typically is not a pH player if there's anything else that's stronger than water in that. So next thing we're going to do is figure out the initial number of moles of each pH player. So in this case, just the HClO4 and the LiOH. So for the HClO4, to find the moles, or we're actually going to do millimoles, we're going to do volume times concentration for each substance. So for the HClO4, according to our problem there's 10 milliliters of the HClO4, and we're just going to multiply that by its concentration, which is 0.3 moles per liter. And so that's going to be 3 millimoles of that. If you want to work in moles, that's fine as well. You just need to convert your milliliter amount to liters. You divide it by 1,000. I personally just find it easier. I like to be a little bit lazy sometimes. I just leave my volumes in milliliters. That just means I'm working in millimoles then when I get to this particular part. All right, and so we'll do the same thing for the lithium hydroxide. We've got 75 milliliters of that one, and we're going to multiply that by its concentration, which is 0.2 moles per liter, and that comes out to 15 millimoles. All right, and so it's those amounts that we're going to use in the ice calculation. Now, this is what I like to call a different kind of ice calculation, because instead of using concentration, which you can use, I like to use moles for this particular part. The issue with using concentration, it works. You've got to use the concentration after everything gets mixed. So, for example, we would need to convert these millimole amounts back into the combined volume concentration of the 10 and 75 milliliters. Now, we're going to do that a little bit later on, but it's not absolutely necessary to do it in this particular step. So we'll put our 3 millimoles of the HClO4 here, the 15 millimoles of the lithium hydroxide here. And again, if you've watched some of my other videos, you've seen these other ice calculations where we use X for the change. We do that for equilibrium systems. This, however, is not an equilibrium. If you'll notice here, I put in just a single arrow. This is, for all intents and purposes, a one-way reaction, not really an equilibrium. That means these substances are going to react and make as much product as they possibly can, limited only by one or the other of these substances. When one of them runs out, that's when the reaction stops. So here's how you get your change. The change will always be the smaller of your two reactant amounts. In this case, that's the 3 millimoles that I have here. So I'm going to decrease by 3 millimoles here, and I decrease by 3 millimoles there. All right, you've got to have the same change across the board. For anything that's decreasing, your reactants are going to decrease. Products, if we were keeping track of any of those, would increase. But here, there's no products that we need to worry about. They're there, but they're just spectator ions. It's just the strong acid and strong base that affect the pH here. So what happens to the HClO4? 3 minus 3 takes it all the way down to 0 millimoles. There's no perchloric acid left. And then 15 minus 3, that means I've got 12 millimoles of that lithium hydroxide. So what we just did is this ice calculation where your change is the smallest number of moles. All right, one of the two reactants should go to 0. All right, if it's an equivalence point system, then your initial amounts would be the same. Both reactants would go to 0. And then some other things happen there. But this is just to give you another example here. Number 5 then says, determine the concentration of any remaining pH player, if there are any. And we do have a remaining pH player. That's the 12 millimoles of lithium hydroxide. So to find that concentration of lithium hydroxide, to show concentration, we put it inside of square brackets. You're going to take your millimole amount, the 12 millimoles that we have there, and we're going to divide it by the total volume. All we need to do is add the 10 and the 75 together. That gets us 85 milliliters of that. So the 12 millimoles that we have left over that didn't react are now in 85 milliliters of solution. And I did this a little bit earlier. That gives us 0.14 moles per liter of lithium hydroxide. So essentially what we have left is this strong base with some salt that doesn't affect the pH, with some ions. The lithium ions are there, the perchlorate ions are there, but neither of those affect the pH. The only pH player that affects the pH here is that lithium hydroxide. So the next step, we're going to take the negative log of that strong base concentration. And when I do that, I get 0.85. Now, as you've heard me say in some of my lecture notes, whenever you take the negative log of something, you want to ask yourself, is that a pH or is that a POH? And in this case, since it's the negative log of a strong base, that means we're going to get the POH. That's the hydroxide ion concentration. The power of that's what the P stands for in POH, is the power of hydroxide is 0.85. And so then really easy to get us to pH, we just subtract that number from 14. That's always our relationship between pH and POH. The sum of those is always 14. And so there's our answer, 3.15 for this. All right, so pretty straightforward. And again, you can use those same 6 steps for really any strong acid, strong base. Now, again, we'll look at some examples in another video that looks at what if we have a product left over in there, and that can affect the pH as well. All right, that happens when you've got a weak substance as one of the reactants in that case. All right, but that's it for this video, so I'll see you in the next one.